Okay, seems you hear me. My name is Sarem, and I'm from Aarhus University. I work with Lies Wolfson de Jong and Mons Greve. Madeleine yesterday very well highlighted the importance of incorporating domain knowledge into machine learning. And that's actually the topic of my PhD in Denmark, where I try to develop a spectroscopic and digital soil mapping models using this what's called physics-based or physics-informed machine learning model on some of the soil properties that are highly related to soil health. So, this way. So I start with this diagram. If we consider the problems that we have in science in terms of available data and also known physics, we can distinguish some categories. Like, for example, there are problems that we know a lot of physics, we have a lot of data for them, and the cost of getting data is very low, like large language models, speech recognition, so you can easily get your data on top. So for these problems, we can go with a pure data-driven model. There are also problems that we have a very good understanding of physics, like laws of motion, perhaps. So for these problems, also we can go with physics-based models, but it seems that in soil science and many engineering problems, we are somewhere in between. Well, we have some data and we have some partial understanding of our systems or soils. So over the last couple of years, a new branch emerged, which is called physics-informed machine learning, that tries to combine both, tries to bring in domain knowledge into machine learning so we can enjoy the benefits of both extremes. Like we can have the flexibility of data-driven models, but still with trained models that generalize better. And I will explain today that how we use this for estimating soil particle size distribution using soil spectra. Particle size distribution determines pore size distribution, so it determines also water and air movement in soil. It's a very important property. It also determines plant available water, is highly tied with soil compaction. So it's very important to be able to estimate this soil texture or soil particle size distribution using a fast method. So we have been using spectroscopy methods for some years. What we do basically is that we get the spectra. This is the conventional method that we get the spectra, we feed it into a machine learning model, then we get sand, silt, clay, what we call it soil fractions. But the problem is that this sand, silt, clay do not represent exactly the entire particle size distribution. For many applications, we need the entire particle size distribution, not just sand, silt, clay. The other problem is that we have different soil definition systems. Like, for example, if I am going to gather data from different countries, in Denmark, we consider silt as particles between 2 microns to 20 microns. In US, it is 2 to 50. In some other countries, 2 to 63 microns. So we always need to do some kind of data harmonization and interpolation. So we need to accept some sort of error. So we need to have the data in a unique system. And again, another challenge is that when we make predictions, those predictions are still in the same system, the input system. So, but what are these particle fractions? Actually, this is an example of soil particle size distribution. It determines the cumulative fractions of particles less than a specific size. So it's just a curve, a cumulative curve. So if we have the curve, we can calculate any fraction that we want. So, for example, sand, silt, clay in any system that we have. Our goal was to, our goal was to just not estimate sand, silt fraction, just to get the entire curve from out of machine learning and out of a spectrum. So we designed a neural network that its main input is the soil spectra. So we added particle size as an extra input. So what we get in this case, in the output layer, is the cumulative fraction at that particle size. So it basically means that if you train this neural network it should learn this relation between particle size and the cumulative fraction. It should learn this curve. And we solve many of the problems. But the saddest story is that if we use a conventional method, a conventional machine learning model, it can produce something quite meaningless because we just try to close the measurements to the predictions. It has no sense of the shape of this curve. So what we do here is where it comes physics. So we try to incorporate some physics into the machine learning to help it to learn a bit. And that's not rocket science. It's not just very sophisticated physics. It's just very basic kind of things that we can incorporate. The first fact that we know about this cumulative curve is that it's always increasing. So nobody expects that the curve at some point goes down. So it should be always increasing. So we force the neural network to always remain increasing. We also know that when we get to the maximum particle size, it should add to 100. That's a basic fact. Then again, we put a constraint and help the machine learning to understand this. Also, we know that even for very, very fine particles, it cannot be negative. So a negative cumulative particle size doesn't have any meaning. So we again put another constraint. So we have these three basic physical constraints in this method, and we have different options about how to incorporate this. We cannot just talk to a machine learning model. We need to somehow implement them. There are different ways. For example, if we want to force the model to reach 100, we can penalize in the loss function. So we change the loss function. The other two physical constraints, we use a specific activation functions inside the model to learn. So I just want to say that there are different options in how to inject this domain knowledge into the machine learning model. So to test our proposed approach, we measured reflectance spectra of close to 2,800 samples in Denmark. For these samples, we also had the sieve and hydrometry data of particle size distribution. So we trained our machine learning model. So we don't use actually the raw data, just in parentheses. Normally, we apply a retreatment to that, and then we apply a principal component because spectra is a very high dimensional data. And then we train that neural network using this physics-informed method. And here you can see how the solution evolves during training and try to find the shape of this curve without limiting it to a specific form. The point is that during training, it sticks to the constraint that we put. It always remains increasing. It reaches to 100, and also it never produces negative values. Normally we see just the solution of a machine learning model. I always like to visualize this because it helps me understand what's happening. As you can see here, also some results for other soils. The good point about neural networks is that it's a continuous function. It's not just like a random forest that is discrete. So you can take the derivative to determine the probability distribution, which is more familiar to people. And we can model different kind of shapes. So when you get the entire curve, then you can calculate sand, silt, clay in any system that you want. So you don't need to suffer from those kind of interpolations, etc. And yeah, in here you can see that the model also works very well, even though prediction accuracy was not our main interest in this work, but results were very good. Here also you can see some examples of a conventional machine learning model, a physics uninformed version, that I removed the monotonicity constraint. You can see at some point the curve goes down or on top there, because a machine learning model does not have any understanding of how it should be. So it can produce something quite meaningless. Or here, if you remove the constraint for maximum particle size, it doesn't reach to 100 in some samples. So this is what we did for soil spectroscopy. So now we can get the estimation of the entire curve. We use this for a spectroscopy, but the same concepts can be applied for digital mapping of soil texture. For example, if you want to develop a global map of texture, then we can do this. And it works very well because then we don't need to do a lot of this harmonization. We have done a similar work, but because time was limited, I skipped that. But I just showed to you that we also estimate the entire retention curve from soil spectra and also some other soil basic properties. This is soil water retention curve that determines water content versus soil suction. It's also very important property for us. And the good point is that with this new method, we can keep samples with partially measured data in the training set, capability which was not possible with conventional methods. So we can keep these samples in our data sets. So yeah, if it's a mapping exercise, then we can keep the spatial coverage. We don't lose any kind of data. And it's very difficult to obtain or measure a soil hydraulic property. So it's important to keep this data in the training set. And yeah, our goal is to estimate a very fast approximation of these two fundamental curves from just one scan of soil. So you can get information about it. A preprint of our work on particle size distribution will be available next week, but we have also published a work on soil retention curve using these physics-informed methods. The same concepts there for the transfer functions. If you're interested, you can have a look. Also, recently, together with Budim and Minosny, we wrote a review paper on different ways that we incorporate this domain knowledge into training of a machine learning model. That was my talk, and with this nice quote, which I couldn't find a source for it, then I finished my presentation. Thank you.